request from Mark asks if anyone has an analog video cable, which when I was a lad we used to call a video cable or a VGA, like a VGA, and perhaps even a computer power cord. And a special request for a computer power cord. All right, then we'll set this up. And from merry old England, folks who can't be here today, one fellow sent me a link to a Forth related project. I posted that link onto flynn.zork.net/tilde/JV/Forth Day. So you can interpret that, check out the link. And gentlemen, here is Vasa with t-shirts for you all.
Thank you. I'd just like to quickly mention that we still have leftover the t-shirts like the size L and XL. It's just $10 if you want. Let me know. And I just want to have a feel if we have a new design. How many of you would be interested? Maybe for the next. Please raise a hand.
Darker shirts that make us look slimmer.
Okay, is that okay? Let's just. Can I see the hand once again? Like how many?
Something that doesn't show coffee stains.
Okay, coffee stains. Okay. Well, thank you. If somebody has a good design, let me know. Okay, and we'll actually think about it. Okay. Thank you. That's all.
I'm on. Remember to wear a lapel next time. Ready? All right. Hi, I'm Leon Wagner from Forth Inc. And I've had the pleasure and luxury of programming in Forth since 1984 with no interruption. And I'm going to talk to you today about an implementation we just did of Forth on the ARM Cortex M1. And there's been a lot of discussion about the Cortex M series I've noticed on your mail list lately. There's a whole series of Cortex M processors from ARM Limited. The M0 is sort of the little baby one. It's an ARM v6 instruction set. And they're really nice. You can get these little Cortex M0s for about $1 a piece. Full 32-bit, everything. And I honestly can't understand why anyone would use an 8051 anymore if you can get one of these for $1. The Cortex M3 is, huh? Installed base, most of the universe. Lots of toasters and things use them. Cars, 8051s. The Cortex M3 adds an extension to the instruction set and becomes a V7M. And it has a bunch of things that are interesting to me. They look like they're interesting to people who write C compilers. The M1 exists not as a silicon part, but actually just as IP, and it's to be instantiated into FPGAs, ASICs, and things like that. And that's what I'm going to talk to you about today. I have a paper. I actually printed this up if you want to pass these around. I've got 40 copies because that's exactly the only amount that would fit in my... I need a volunteer. You. Thank you for that, Kevin. And I didn't put any contact info on it, unfortunately, so I've got business cards if anybody wants. I'll just leave a stack of them. And I love getting emails from people with questions. I also have it posted on our website if you want to just grab a copy you prefer to follow in the PDF. It's right there at forth.com. Download cm1.pdf. What we encounter in a lot of the projects that we work on is that we will have a CPU on our board, and we'll also have an FPGA or more than one FPGA that's performing the sort of proprietary logic functions of the project. I drew this very simplified drawing of what we see on the board, and we have multiple connections going between the CPU and the FPGA. These 8 lines are actually representative of all the buses that are going back and forth between the two parts. Typically, you'll have a data bus, and most of the things we're seeing these days, that'll be 32 bits. And some address lines, depending upon how many registers there are. There could be as few as 3 or 4, but if you're talking about accessing dual-port block RAM in the FPGA, then you're getting up into the 20, 24 address lines, and there will be control lines, read, write, output enable, byte enables, that sort of thing. And by the time you're done, you've got 60 or 72 lines running between these two parts. And you have all the logic that you need on the FPGA side to do a full-on bus interface to talk to the CPU. So that's a lot of real estate on your board. We were originally approached to do this a few years ago by NASA because what they wanted to do was not have to find both a rad-hard FPGA or ASIC and a rad-hard CPU and then go through all the complexity of laying out these boards because of their space and power constraints. So they had decided to put the CPU inside the FPGA, as a lot of people are doing. Here's my animation. So what I'm going to talk to you about is how we've done that in this case. A couple of years ago, I talked to you about the version we did that used a cold-fire CPU core and put it inside the FPGA. And since then, they realized that the cold-fire was taking up quite a bit too much real estate in the FPGA. And they wanted to go with something better. And just recently, NASA's crack team of lawyers have finally finished negotiating all of the IP things, and they have a full license to the entire ARM Limited IP library. So we've actually put this on the Cortex M1 on an FPGA for them. There's a whole bunch of FPGA softcores that are out there. The MicroBlaze and PicoBlaze, those are proprietary and they're limited to Xilinx devices. The Neos 2, which is proprietary, limited to Altera devices. The Lattice Mico 32 and Lattice Mico 8. Has anyone ever used these? Any of these? No? I've got some experience with the MicroBlaze. James does too, I think. The Lattice ones are interesting in that they have an open source license. They're not proprietary, but it turns out they're heavily optimized for Lattice devices, and woe to you if you try to use them on something else. I only put this last one on because I really love the name, the Leon. And they're up to I think the 4 now. There was a Leon 1, Leon 2, Leon 3, Leon 4, and we like that. And it's a SPARC V8 instruction set. Now, one doesn't ordinarily think of a SPARC for a deeply embedded application that's going to fit in something tiny. And naturally enough, it's so bloaty that it doesn't really work in practice. But there are multiple licensing models. You can get both open source and proprietary licensing. It's described in synthesizable VHDL. And it was originally developed by the European Space Agency. So that's another reason that it might be so big. But the name wins. The cold-fire core that I talked to you about before, and it's available in V1, V2, and V4 cores. If you know the cold-fire, each of those adds things to the instruction set. But the V1 is the core that you really need. That's a proprietary license. It tends to be a bit expensive. It has a standard instruction set, the cold-fire, which is very common and very popular, and actually quite pleasant to program in. The one that I demoed, the V1 core, running on this board, the Altera Cyclone 3 evaluation board 2 years ago, its max clock speed appears to be about 40 megahertz. It kind of tips over if you try to push it past that. And it uses about 29% of all the available space of the logic and RAM available in the Cyclone 3. The microcore. Has anyone followed the microcore project? It's really kind of interesting. It's developed by Klaus Schleissig, whom I think many of you know. Many of you do know Klaus, right? He used to live here. I have a picture of him coming up. He has a very interesting license, and if you go to his website, I think it's microcore.org, he has the Microcore Exploratory License. It's a very, very interesting license agreement. Basically, if he gives you permission, you can do what you want with it, but he has to give you permission. It's described in synthesizable VHDL because Klaus likes VHDL. And the instruction set, unlike all these others, is a native 4th instruction set. And for those of you who remember Klaus, here we are having dinner, and he's making a point. Is
he second from the right?
What? That's me. Jet lagged out of my mind. This is Klaus. He's next to me, staring at me. Bill Stoddard on the left and Stephen Peltz on the right.
How come he got so old?
Who? Klaus? Klaus was hit by a car 3 years ago while crossing the street, and he has the permanent imprint of an Audi A6 in his leg. He is now able to walk, but with difficulty.
Well, of course, we all need to know because he was here 25 years ago.
Yeah. Klaus he's one of my favorite people. One of the reasons I go to Euroforth is to see Klaus. So today I'm going to talk to you about the Cortex M1. It's proprietary, it's ARM limited, you have to license it. There's a free evaluation license available, which I started with, and it gives you 90 days to tinker with it. Mine expired on Monday. That's another story I'll tell you about later. The really nice thing is that it's vendor independent. It runs on just about anything you can put it on. And it's distributed as, did I put that on here? It's distributed as encrypted Verilog. So the license key lets you unlock the encrypted Verilog to include it in your design. It runs on FPGAs, ASICs, ASPs, anything you want to put it on. It's an industry standard processor. The Cortex M series is very widely supported by an enormous system of tools.
Can you then read the Verilog or just
No,
it?
all you can do is compile it. So you can't modify it. I know. But this is the restriction we have to live with.
You can't modify it without other steps.
Without other, okay, but I can't comment on that. There's a huge ecosystem of tools available for this. You know, there's all the typical C tools. There's a, GCC works with it. There are several Forth implementations that run on it, including ours, including the one from MPE. VFX runs on it. Probably G-Forth will run on it with a little bit of tweaking. And the really nice thing that NASA liked about this compared to the Coldfire one is that it's fast and small. And here's a few comparisons. The bottom one is interesting. I've gotten this up to 120 megahertz on this board, and it only uses 14% of the FPGA, and it actually gave me a little bit better, a few more resources that were available to me while I was programming. So, it's way better than the Coldfire. And it uses the ARM v6m instruction set. In order to do the demo that I'm doing here, you can actually build one at home. You need SwiftX for the ARM, which you can download free from us. The Quartus 2 Web Edition, which you can download from Altera. The Cortex M1 FPGA Development Kit, which you can get from ARM Limited. The Cyclone 3 Starter Kit, unfortunately, it's not free, but you can get one from Altera. And it's pretty cheap. It's 199 bucks, and there's a lot of nice stuff that you can do with it. And you need a serial port. And that's this little tiny board. The legacy ARM processors, the ARM 7 and ARM 9s that we had supported in the past, we would just use a JTAG interface to do our debugging on. Because it had something very nice called the DCC, the debug communication channel that wrote along on the JTAG. For some reason, ARM decided that we don't need that, and they took it out. So the only way you can do JTAG debugging on a Cortex M series, and if someone knows a better way, please tell me, but what I've come up with is that the only way to do it is to go from breakpoint to breakpoint, and the only way you can access memory or registers is with the CPU halted. And I'm sorry, that's not real time. So we don't do it that way. So I brought some pins out to the board, and I hooked a serial port up to it, and my debug interface is a really fast serial port. And you can get these little breakout boards for 15 bucks from SparkFun. And it's an FTDI chip, and they're the only ones who seem to get this whole USB to serial thing so right that you just plug it in and it works the first time. Greg is smiling at me. We had this conversation a few months ago. So with those things,
Is there going to be a version of that with the USB instead of
well, it is actually USB. I plugged it into the USB cable, and it just comes out as 3-volt TTL on the other side to go to the board. And I think that's the end of the slideshow part. So I'm actually going to show you how we did this. And I'm going to do this in 2 parts. I'll show you how you actually go into the Quartus tool and build the CPU. And then we're going to skip ahead to one that's already built that has all the pin assignments done. So we're not going to go through the tedious part because that takes quite a bit of time. So we will begin by, in this part, if you want to follow along in the paper, this is section 2.1, starting a new design. Launch Quartus 2. Well, I have these web pages open just to show you where these various pieces are. Here's the Cortex M1 page, the M1 development kit. If you want a visual cue and you're actually going to look for this and try it yourself. The Quartus 2 web edition is available in both Windows and Linux versions. It's huge. It's 2.5 gigabytes of download. And oddly, the Linux version is bigger. It's 3 gigabytes of download, which I thought was interesting. This is the download page for all of our eval versions, which are free. The ARM is on there. Oh, the ARM's the first one on there. There's a whole bunch of other ones, too. Here's that little FTDI board, if you, that's what it really looks like. That's the one here on the desk. Those are nice. And then the Cyclone 3 eval kit. And here's sort of a list of everything you get with it. End of that. So over here in the Quartus 2 environment, we're going to start a new project. And of course, there's a wizard for that. And I'm going to put this in I apologize for my typing. I spilled something in my keyboard a few weeks ago, and pretty much the whole left 2 columns of keys are sticking. The name of the project will be CM1, short for Cortex M1. I don't like to type, so that's what I'm going to call it. And you have to name the top-level design, and the convention is that you just append underscore top to it. At least that's what a lot of the designers I see do, so I copy them because I don't know what I'm doing. Yes, we'll create it. We don't need to add any files to this just yet. We need to choose a part. I'm going to cheat because I know that it's a 324 pin package. And it's this first one. Say next. Those all look fine to me. We're done. So we've created our project. We'll go on to the SOPC Builder, System on a Programmable Chip. Tools, SOPC Builder. That launches. We wait. This is a fast computer. It really takes a lot longer if you have a real hard drive. When this finally launches, what we're going to do with it is we're going to add the Cortex M1 core and a few pieces to it and connect them all together. Well, we have to name this. We're going to name it CM1. Do not, under any circumstances, name this the same as your top-level design, because it will try to promote the output of SOPC Builder to be the top level. It would be very nice if you could do that, but you actually have to make a little bit of a top-level design to sit on top of it to hook a few things together. I tried it the first way originally, not good. And this is all in Verilog, so we'll leave the setting in Verilog. And here we are. So we'll make that full size. This resolution is fine. So we're going to add some things to it. The first thing we need is a Cortex M1 processor. And that's going to pop up a little configuration box, and here's the Cortex M1. Oh, look, Buy Now is the first thing that's default highlighted. We're going to disable debug because we don't want to waste the space on that JTAG module that wants us to put breakpoints in. We're not going to use it. Number of IRQs is set to 8. We're really only going to use 1, but maybe we'll add some later, so I'll leave that set to 8. There's 2 kinds of memory, code memory and data memory. Or I'm sorry, instruction memory and data memory that are actually tightly coupled memories, so they're built in here, and it's basically zero weight state memory that'll be built out of the fabric of the FPGA. What size do I want this to be? Let's say 16K for both of them. And I'm going to say yes, I want to initialize the contents. And this file, this hex file, that's the output from the 4th compiler. So that'll actually be built into the initial design. So when the thing starts up, it already has the 4th kernel built into it. And there was one more option here. I do not want this memory to be read-only because we know what we're doing, and we're going to write definitions in real time, and we have to be able to write to the code memory. But we'll say finish. So that's part 1. We need some parallel I/O. Down here in the list, we'll pop open peripherals, microcontroller peripherals, PIO. We're going to add some PIO to it. We're going to say it's both input and output. And that's going to be for, on the board you can see there are some switches and some LEDs. And my nifty demo, of course, is going to read the switches and blink the LEDs, because that's what we do. And there's a couple of options on here I want to set. No, I think that's it. So we've set them to input and output. I only need four ins and 4 outs, so I'll do that. Cut down my space. And then, of course, we need a debug interface. We want a UART. And oddly, that's called an interface protocol. Just a plain old UART. And no parity 8 bits, 1 stop bit, blah, blah, blah. 115.2 is a perfectly fine speed. Because of the clock weight we're running at, that divides down nicely. We'd like to go faster, but then we'd have to add a PLL. And here's the gotcha. The default for this is called accelerator use divisor equal to. No, because my clock rate is 50 megahertz, and this would give me a 25 megahertz UART. So we want to use actual. It took a long time because they hid that below the fold. It took me a long time to find that. Why doesn't this work? Okay, having done all that, connect it together. Where's the clock? The filters. I'm going to see all the interfaces, including the clock. So here's the clock, and the clock is going to go to the input of the Cortex M, and it's going to go to the PIO, and it's going to go to the input of the UART. The bus master from the Cortex M needs to go to the PIO because we want to read and write its registers, and it needs to go to the UART because we want to read and write its registers. And the UART is a nice UART, and it gives us an interrupt. So we have that connected back to the IRQ of the CPU. Oops, where did that clock on go? And there, we're all done. Looks good. The IRQ is here. That looks fine. You can set some base addresses. I'm not going to do this now because my final design has it, but you want to have base addresses that are in the peripheral space of the CPU. And then when you're all done, you click the generate button, and when it's done, it says compilation successful, and it leaves you with something you can work with in the top level design, which we will skip ahead to. So I'm going to go over to my pre-built. This is like one of those cooking shows where the chef gets everything together, and then you bring out the finished results that the assistant have done the night before. Here we go. So I have another one that I've already built, and I'll pop it open, and I'll just show you the things that you have to do to complete this. After you've generated that design, you have to do one pass of analysis and elaboration. And what that's going to do is it's going to figure out where all the things are that you actually need to connect to the outside world, and then you assign the pins to it using the assignment editor. So having done that, if we look at the assignment editor, we can see the actual things that have been assigned. Over here on the right, here are the labels that come from within the logic, and then there are the actual pins in the outside world that I've connected them to. And here's how I know that. With the board came this wonderful Excel spreadsheet. It goes down, 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 and you can see all the things that are connected on the board. And the right column gives you the actual pin numbers. It's a 324 pin part. It gives you all the pin numbers, FPGA, that things are connected to. So I picked through that list and found the things that I wanted, and those things are the input ports from the switches, output port bits to the LEDs, transmit and receive for the UART. That's pretty much it. Oh, there's a reset line, because we like to reset our CPUs when they crash. So that's the assignment editor. We also need to make a little tiny top-level design, and I used the schematic entry for it, and this one isn't going to fit up here. But I'll scroll across it, and you can see what I've done is I've just made a few connections into that module, the Cortex M1. There it is. There's a few things you have to tie high and a few things you have to tie low or it doesn't work. You certainly don't want any spurious, non-maskable interrupts coming to you, and you certainly don't want the debug reset to be floating around doing bad things to you. So the two of them get tied high, two of them get tied low. We connect the pins to the outside and we're done. So it's a very simple top-level design. Having done all that and compiled it, we start up the programmer. The programmer is really nice. As soon as you click OK, it moves itself to the background, so you have to go find it. Programmer. And there it is. So through the JTAG interface, the programmer will download the compiled file, which contains all of that logic for the core and the initialization for the instruction memory for our fourth kernel. There it goes. And the core itself is time limited. You can use it for 7 hours, 59 minutes, and 54 seconds, then it will cease to run. When you have the fully licensed version, you can actually just load it into the flash and let it boot from the flash. The license for these is, pardon?
Is there any kind of hobbyist license that is reasonably priced? Educational license?
I don't know. I know that if you contact ARM Limited and say, I would like to talk to you about a license, they will say, here is our NDA. Please sign it and mail it to our offices in the UK. I'm still waiting for mine to come back. Because when I realized that my eval license expired last Monday and I wanted to actually show this to you, I contacted them and I actually had to fill that out and send it in. They graciously extended my eval license for another week to let me come here and show this to you. The real one that you buy, the actual license that you were to buy for commercial purposes for this board, is only $1,000. That's not bad when you compare it to a lot of these other IP cores that are all in this sort of $20,000, $30,000 range.
J1?
Well, the J1's free.
Well, yeah.
Yeah, I know, I know. However, the purpose for doing this is because this is a NASA project. NASA has to use an accepted core, blah, 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 and they're not going to fly a J1, and they're not going to fly an EP32, and they're, you know, so these are the constraints we live with, and this is why we're doing it. I didn't just do this because it was fun, although it turned out to be fun. So the core is up and running, and we'll go over to our firmware directory, which is where we have our stuff. This little file here, itcm.hex, is the output from the compiler, and that was the file that you saw me refer to earlier that we actually loaded into the design. Now we get to the part in the environment that we're used to using, and here's our SwiftX for the ARM, and we compiled it, and we made a connection, and that little message at the bottom here, SwiftX ARM Cortex M1 Altera, is actually coming from the board through the serial port. So now at this point, I'm connected to the target directly, and I loaded up a little demo, and the last few pages here of the paper are the program listings of the demo. And all I'm doing in the demo is showing you the LEDs and the buttons connected to the outside world via the register interface through the PIO. And it's actually kind of nice because it looks just like... Now let's move this over. So here's the source code. And here's all you do to write to the LEDs. The outputs are inverted, and instead of going through the tedious trouble of putting inverters on all the output pins, I just put an invert in my code. I thought it was easier. So to write to them, because they're active low, you just do an invert, and you write the output to the PIO base register, which is mapped in as memory, and it's a cell. You just do a store to it. My initialization for it is just to turn them all off. So let's try that. The 4 user LEDs are right here. That one that slid up next to it is the power LED. Can you see him? And if the camera can see it. So if we want to write to one of them, that should turn one of them on. Did it? I can't see it. And we can do the next one. Nope. And so on. Okay. And the button tests are in another file. Buttons. Good name. And all I did was just make some constants for the name of the buttons and a test if it's pressed. And those are also active low, so you just AND it with the mask. 0 equal for true. All that gets wrapped up into my little demo program. And that's it. I made a background task so that I could let the demo run concurrently with what I'm doing. And there's a typical full-on fourth multitasker on here, so it's quite nice. And the whole thing that starts it up is this word demo, which initializes the LEDs, sets the speed that we're operating at to medium, and you can see my speeds here. Fast is 50 milliseconds a step, medium is 100 milliseconds a step, slow is 250 milliseconds a step. Totally arbitrary, but you can see the difference when you're running it. And I build the task, and then I just start it up. So let's do that. And it crashed. That's nice. Wow. Oh, did I stop it, or did it stop itself? That's nice. This is the reset. Whoa. I guess I won't show you that part because the CPU stopped running. That's interesting.
8 hours or 8 minutes?
I don't know, it might have been 8 minutes. I'm not going to go through that part again because I'm almost out of time. But at that point, the LEDs will chase back and forth, and you can set the speeds and so on, and you can do that interactively, or you can press the buttons to change the rates that the speeds are running. I wonder if I shorted that out, in which case I'm really dead. If we press cancel on this guy, let's go back and try him again. Start. Please. Uh-oh. I think when I was moving this around, I shorted this guy against here and broke something. What a shame. I know. Practice electrical safety while you're doing demos. It's a good plan. Yeah, exactly. So there you are. You can add more definitions to do this. You can type them in at the command line, and because we made the program memory writable, they're available to execute immediately. And it's a very nice little development environment. The board has a huge chunk of SD-RAM external, and some of those lines you saw in the spreadsheet show how to hook it up, and there's an IP section in there that you can add SD-RAM. You can add a PLL and crank your clock rate up. I just use the default clock rate. There's a lot more things you can do with it. And if you want to try it, you're free to download the pieces and give it a go. Any questions? Yes?
Comment. This will run on the Cyclone 2.
3.
There's another pretty cool development kit. The
Yeah, I've seen it.
Have you seen it?
Yeah, there's another nice one with a Cyclone 3 on it, too. Yeah, I use this because it's out of the box, ready to go on this board. And I also happen to have this board, so there was nothing for me to buy. You know, and I'm kind of cheap, so that's the way it is. Yes?
How prevalent is sports in NASA projects, GPL projects?
There's a great website.
Yeah.
And if you can't find it, send me an email and I'll send you a link. But Google is your friend.
Yeah, there's a page on GSFC, Goddard Space Flight Center, and there's a fairly still active contingent of people who use Forth there. One of them is a guy named Bob Caffrey, who started out, Randy knows Bob, who started out fairly low, and apparently he's now quite important at Goddard Space Flight Center, because the last time I was there, he came to visit the lab, and this buzz went around, Bob Caffrey is here. It was very cool. I'm done. Thanks.
Another note for you speakers. When the guy gets into his Q&A, it's your cue to start putting yourself up here.
Have the cable.
Dave Weiland, you were unable to infer that. So this is your chance to move forward, put your stuff